Thank you. Good afternoon. It's a pleasure to be here. I'm Licia Verde from the Instituto de Ciencias del Cosmos, the University of Barcelona, and I'm crashing this party. I was never actually a student or a postdoc here, but I'm one of those, I think, examples that you see the footprint of an institute, not just out of their staff or their alumni, but even beyond that. So I decided at the last minute to sort of change my talk, because we had two wonderful talks that presented the DESI survey, presented the BAO, presented the Lyman alpha, and then stopped short at the cosmological interpretation. So now I have the privilege to actually walk you through the cosmological interpretation. And so what do I do next? Okay. Do I go here?
Yeah, I guess you can click.
Do it here?
I know that. Yeah. Okay.
Okay. Thank you. Oops. All right. And so you're going to get some presentation of the cosmological interpretation on behalf of the entire DESI collaboration. In case I run short of time, let me show this. This is a major project. There are the sponsor, there are 72 participating institutions, there are more than 800 people, so let's bear this in mind. I like to show this plot. It was created by David Schlegel before actually DESI was planned, and the number there, it's a little bit out of date. It's probably more like 30 million, but in a log plot, everything looks linear and you wouldn't see the difference. What is particularly interesting of this is that 2 good nights or 3 nights of this is this. It's a 2DF, which George mentioned before, and it's something on which I did my entire PhD thesis, and it took many years to do. So that tells you how cosmology evolves. And so the previous talk concentrate mostly on, Andrea Fonto concentrated mostly on the first paper, and I'm going to go straight into the second one. So let's back up a second. There's a lot of physical information that in principle one can learn from large scale structure. From the overall clustering, one can ask all these questions: constituent of matter, physics of inflation, etc., etc. From geometry, the standard ruler, which is the BAO that were introduced before, one can ask the question about what is the expansion history of the universe and go after things like dark energy. There's more, the redshift space distortion, there are the larger scale, there's spectral analysis. So far, the DESI results that are out are only about the BAO. So there's a lot more that one can get out, but let's see what we can do just with that. And so to refresh Cosmology 101, one measures redshift and angles. The standard ruler is set by the physics of the early universe. We believe we know extremely well the physics of the early universe, spectacular success of the cosmic microwave background experiment, and that gives us the length of the standard ruler. And then from there, one can infer distances. This is only background and only expansion history information. So how is the ZBO analysis different? So it's the biggest data set, both in terms of the number and the volume. And it's the first time that a catalog level blind BO analysis was done to mitigate confirmation bias. This was done on the galaxy sample at the catalog level. The Lyman alpha was also blind, but at the summary statistic level, not at the catalog level, but it was also blind. So the catalog level blinding, and I go through this because at the ICC we develop a lot of this idea of the blinding, is we measure redshift and an angle. We always think in distances, and the theory is always in distances. So we always need to assume a redshift to distance relation. We only need to assume a background cosmology before we interpret larger scale structure surveys. And therefore the blinding come in at that level, basically not telling you exactly which cosmology you use to transform redshift into distances, but then keeping that in the back of your mind. There is also a change to the interpretation of the peculiar velocity to redshift to blind the growth rate, and there is a weight-based blinding for primordial non-Gaussianity, but those results are not out yet, so that doesn't affect this analysis. There is a very high statistical significance for the detection of the signal. So the aggregate distance precision through all the redshift is about 0.5%. And this is from 1 year of data, compared with the 20 years from Apache Point of SDSS that got an aggregate 0.64%. So that's what I mean by it's very high statistical significance. And again, it's just the first year. So the first question, and here I take on how the previous talk ended, is the lambda CDM still okay? And this plot shows that, okay, the best fit model is a little bit different from the Planck best fit model, but it seems okay. And so then one can ask about the cosmological parameters. Again, let's remind that since we only do BAO, and we want to assume anything at this level about the early time physics, all the BAO can give us, unless we know the length of the standard ruler, we have to assume the length of the standard ruler, is the combination of standard ruler times little h versus omega mater in a lambda CDM model. That's all the BAO can give you. And at a given redshift, there is a degeneracy between these two parameters. But as different redshifts are added, then the degeneracy can be broken. And on this side, it's zooming in by comparing the DESI BAO compared to the Sloan BAO, the DESI plus Sloan combined BAO, and the comparison with the CMB. So DESI BAO only give omega mater to the 5%, and the standard ruler length in the unit of the large scale structure to 1.3%. Planck gives you RD in a lambda CDM, not in the unit of age, to the 0.2%. So now you know what game one can play. So in the following slide, I will mention a lot plus BBN. And the next talk is going to go through this, but let me just mention this, why this is important. So observation at a later time of light element abundance can be used to interpret what is the physical density of baryons in the universe. And the connection is with BBN. For the analysis with the DESI data, the number that is used for the constraint on omega baryon h square come from this article here that uses this new code that came out in late 2023, the primordial code by Burns and collaborators, that is fast enough that one can marginalize over uncertainties, even the nuclear reaction rate uncertainty. And I want to show that plot to show that the uncertainty is not dominated anymore by the deuterium abundance uncertainty. Start being dominated by the nuclear rate uncertainties. And so this uncertainty were all marginalized, and that's the number that come out. So what about other data, and what about curvature? So let's take one at a time. What about other data? It's in the now omega mater h naught plane. Once we add the information about BBN, then within a lambda CDM, the lambda CDM tells you what is the length of the standard ruler, and therefore now in this axis there's h naught and not h naught times RD. And this is saying that the different data set within lambda CDM are all consistent. And if one open lambda CDM to an extra parameter that is the curvature, well, you know, some degeneracy open up in parameter space, but this is telling us that the universe is still flat after all this year. And so depending on what is the external data sets one consider, whether it's the location of the first peak in the cosmic microwave background, whether it's BBN plus the location of the peak, or the full joint analysis, Planck plus ACT plus lensing and DESI, of course the error bar shrink, but it's still consistent with being flat. let's zoom in on the curvature, and we can appreciate the usual early versus late time complementarity of how combining early and late breaks the degeneracies. So, okay, and now we go and look at the other component of the curvature instead of if it's deviation from being a cosmological constant. The simplest parametrization is to say, well, there is an equation of state of dark energy. There is an equation of state that also has got a parameter. It's the parameter, it's W. It's considered to be constant in redshift. It's not particularly well motivated, but if you want to consider deviation from your baseline, that's one way of doing this. And in this plot, we see again the omega matter versus this equation of state for dark energy parameters and the various combination with the degeneracy. You see the cosmic microwave background is the purple banana. And the DESI only BAO is that blue constraint in the middle. So one can constrain mostly omega matter, but there's some constraint on W2. And then the supernovae constraints come in yet another direction in parameter space. And then one can combine and break the degeneracy. It's the usual game that we play in cosmology and end up with a tiny little ellipse center around the value that W has in lambda CDM model, which is -1. Okay. So now let's open parameter space even more and say, and using this so-called WWA parameterization, now the equation of state for dark energy parameter is not constant in redshift, it linearly depends on redshift, and then some things start happening. So this on the left is a little bit of a busy plot. The DESI BAO only constraint are the dash black line. And I should show that there is a prior inbuilt there because you want to keep a positive dark energy all the time. So then there's the prior there, and the constraint tends to eat the prior. And one can combine the DESI only constraint with other data set, for example, with the cosmic microwave background or with 3 different type of supernovae data. And on the right-hand side is a little bit of a less busy plot where you can see the whole constraints, BAO plus cosmic microwave background for each of the different supernovae data separately. The supernovae data are not completely independent from each other, so that's why you can't combine all of them. And this is what captured the attention of a lot of the public and many of the readers, because with the Pantheon Plus, which is the most established data set of the supernovae that has been around for quite a long time, is only 2.5 sigma away from what we expect from a lambda CDM model. With the other 2 supernova sample, then this grows to 3.5 sigma, 3.9 sigma. So what's going on? So let's concentrate on this plot. So and deconstruct a little bit the constraint. As before, the DESI BAO only are the dashed black line, and the CMB, no lensing and with lensing, just in case there's something going on with lensing, is the green and the blue that you almost don't see. So you can already see that the CMB constraints, once you take this multi-dimensional parameter space with long degeneracy and you project it down to few dimensions, gives you that triangle, which is not really centered around where you expect -1 and 0, but this is usually happen when you have big degeneracy in a high dimensional parameter space. So when you combine the 2 data sets, then you get something like this. And so you could say, remember there's a prior there, so you could say, it's the CMB fault, because the ZBAO alone is perfectly consistent with lambda CDM. But then you can look at the supernovae instead. So in this plot, never mind the color scheme, now the DESI BAO only is the blue, and the DESI plus SDSS BAO is the green. Why is the SDSS added? Because at around redshift 0.6 and 0.8, the SDSS has still statistical power to add to DESI. There is a correlation between the two. They are observing in part the same sky. The correlation is taken into account there. So that's why it's useful to add SDSS there. And you see they are consistent, but things shift around a little bit because, well, there's cosmic variance. So you do expect things to shift around a little bit. And you see how the supernova data come in a different direction in parameter space, and the supernova data are also a little bit shifted. So you could say, and that's a usual prior, you could say it's a supernova fault. Yeah, thank you. And so what's going on here? So in the left-hand side, you see some parameterization of the expansion history. The Planck lambda CDM, it's the red one. And then the blue, orange, and green are the reconstructed expansion history from the BOSS BAO data, lambda CDM in blue, WCDM in orange, and this WWA CDM in green. And so let's zoom into it on the right-hand side with the actual data in there. And let's see if this... So this Lyman alpha say, it wasn't me, of what's going on there. And this says, it wasn't me, I'm also sitting on the lambda CDM. And this says, it's the LRG's fault, and this one. And this says, it wasn't me, but the one say, you are weird too. Because here I show you the projection in the H of Z, which is the line of sight. But we know, I mean, you've probably seen it from the previous plot, that this guy is weird in one projection, and this one is weird in the other projection of the BAO. So there's something going on there, and it's where SDSS still has got more statistical power. So that's why when you combine with the SDSS, combining with the right cross-correlation and covariance, then the contour shift a little bit. Okay. So here we see again what's going on now in the two projection. And the two fits you can see depending if you do to DESI alone or to DESI plus CMB plus the supernovae. These are these two lines. So in this projection is tried to fit the red point that is which is a little bit low, this projection. And in this projection is tried to fit the yellow point that is a little bit high. And those are the 2 points that we know are somewhat strange. But are they really strange? We have 7 points, and we're plotting 1 sigma. 1 sigma means that 1 out of 3 times you're supposed to be away from 1 sigma. So maybe this is not, too unexpected. So let me move on, because I'm sure you will want to hear something about H0, but everything you wanted to know about the H0 and never dare to ask, I wrote it there, everything I know, and in that review. And this is for George. George says that we need to park H0, and I won't attempt to park this one. I'm from Venice, and I can't park cars. If it was a gondola, maybe, but a car, definitely not. So let's see what is the DESI view on H0. So again, if we take BAO only, we can only have this combination of RD times H versus omega mater, and the constraints for a lambda CDM are small. As you extend the parameter space, then they become bigger and bigger potatoes in parameter space. So you can decide how to break that degeneracy and then get H0. And this is the usual whiskers plot, H0, and then the various dataset combination. This is early time CMB. We know it's around 67, pushing only up to 68. This is the usual late time universe, directly distance redshift relation, TRGB by the Chicago Carnegie Hubble project. This is the shoes determination. This is the SDSS BAO plus BBN. We knew about that already. This is the DESI BAO various combination with the BBN only, with BBN plus the position of the first peak, with the RD from the CMB. This is only, it doesn't take into account the full covariance with the cosmological parameters. The way to do that is just to do it with joint analysis with the CMB. So yes, it's a little bit higher than the CMB alone, but not as high as what we get from the shoes collaboration. So H, it's measured at the 1.2%, and it's still consistent with the CMB, and it's in more than 3 sigma tension with the shoes result, even if we don't look at the CMB. And since I need to move on and conclude, I'm just showing you, just mention something about neutrinos. You've heard about neutrinos constraint from DESI. Again, BA only, only background. We can't see a specific signature of the neutrino mass. The effect of neutrino mass on larger scale structure, we always learn from school that it's this suppression due to free streaming. This is if you fix all the cosmological parameter and just change the neutrino mass. But when you are doing a joint analysis with the CMB, you need to move along the CMB, the degeneracy of cosmological parameters, and then see what's the effect on the larger scale structure. And the effect is given by this solid line here. You see, it's basically an overall suppression and some tiny effect on the BAO. So what we are doing here is just breaking the CMB degeneracy that affect the expansion history of the universe and interpreting that as a constraint on neutrino properties. So for n effective, which is another parameter people are interested in, CMB plus DESI BAO give you a constraint on how many extra neutrino you can get. And it's nice that you can now do that from BBN only and the abundance of light elements, and you get an error bar that is not that different and a constraint that is completely consistent, but it's a completely different ballgame. So coming back to DESI, the constraint on the sum of neutrino masses start becoming extremely stringent. And remember the mass limit for between normal and inverted hierarchy, it's at 0.1 eV. But I would say this is prior dependent and model dependent. We have not seen the signature of neutrino masses. So let me go to the summary. DESI plus BBN give you a 1% constraint level, 1% level constraint on H naught, still in tension with shoes, without even considering CMB data. There are tight constraints of curvature. The universe is still flat. W is still -1. The WWA parameterization give you something there. See the appendix of the paper, not the popular press. There are tight limits on the sum of neutrino masses, but I would not recommend to interpret it as a constraint on the property of neutrinos. It's just an extension of a model and an extra parameter. The most precise BAO measurement to 0.5%, the first BAO blind analysis at the catalog level, the highest precision at redshift above 0.8 because of the ELG, the first significant BAO detection from the ELG and cosmology with them. And these are the future because they are at high redshift, because you can scan a very, very, very large volume. The future for the BAO. And I leave you this there as my conclusion and a plot of the distances as measured from the DESI BAO with a lambda CDM from Planck. This is not a fit to the data. And I stop here. Thank you.
Thank you very much.